Welcome back to another lecture on chemistry. Today we're doing section 1 of chapter 16, and a lot of it is definitional. More than definitional, it's going beyond the definitions to try to kind of get you up to speed on what these terms mean. You're going to see that there's a lot of terms in this chapter that are familiar to you, but they have very specific definitions in chemistry, so they're kind of unlike the way you normally would use these words or these terms. So my goal here is to, in combination with you reading the chapter, going ahead and giving you kind of some examples of how these things might be a little different than you normally would use them, how these terms would be used differently in chemistry. We just kind of, in general, we tend to make some of these terms kind of mean things that they don't, at least not in science. And so that's going to be our goal here today. So we'll go through a few slides. We're not going to go through all the slides in this PowerPoint, just the ones that pertain to the first section. But I'm probably going to expand on definitions even as we go. So chapter 11 here is on energy. And it's energy in chemical systems, pretty much. But even before we start talking about energy related to chemical systems or chemistry, we need to look at this as we need to get some information here and some context to how we use these terms when it comes to science and chemistry. So as far as energy is concerned, we're going to use the capital letter E to represent energy, but we want to know what it is. So first off, let's go at the definition. And here's the official definition of energy in science. Energy is the potential to do work. Okay, that's your definition right there. If you're like me, you might sit there and go, okay, I can put that down on a test, or if there's a multiple choice quiz. What's the definition of energy? I could go ahead and answer that. I can memorize that. But what does that mean? The potential to do work. We also have to realize that work has a different definition also in science, and is looked at a little differently. Okay. So first, let's go ahead and define work. Then we'll define energy. Then we'll see how energy is the potential to do that work. In science, if you take a physics class, in physics, you're going to find that work is not just, oh yeah, well, I'm going to go, to the grocery store and I'm going to box things, or I'm going to be a cashier, or I'm going to go to McDonald's and put, bag stuff and charge people for it. That's what we think of work, right? Or digging holes or whatever it might be. That's in the general sense. But work in the scientific sense is basically this. Work is the force applied over a distance. So if I have like a little box that doesn't weigh much and I push it, I'm not doing a lot of work. It's not making me do a lot of exertion, right? So we say that we do very little work. So there's actually an equation that will calculate the work we've done. Capital W represents work, and that's going to equal to F, which represents force, times D, the distance that we applied that force. So if I take the little box, and let's say I put a Newton of force in, which is really not a lot of work. Basically, it's pushing a box of paper clips is probably what you need, probably about a Newton. And if you apply it over a distance, let's say it's 1 meter, right, across the table, then that would be how much work you did. And so 1 Newton times 1 meter is 1 unit of work. Okay. If I had to push a much heavier object, if I had to apply much more force, let's say a refrigerator, even though it has wheels, those refrigerators can be kind of much heavier to push. So if I had a refrigerator and I had to push it 30 yards, first off, every yard that I push it, or I should say meters, since we're using science, every meter I push it, it's going to be much harder to push than like a little box of paper clips, right? So I'm pushing that thing, I'm doing more force, and I'm doing over a larger distance, say 30 meters. Now the force times distance is going to calculate how much energy I used in order to do that. Okay, so work is a form of energy. Work is a way of transferring energy. I'm transferring the energy I have into the object in order to get it to move. Okay, so that is what work is. And energy is the potential to do that. Now notice the word potential in it right here. Potential means you can do it, but you don't have to. So it's kind of the potential to be able to do that. You could have that inside of you, you have some energy inside of you that can actually go ahead and do that. Kind of an abstract way of looking at it, right? And the definition is a little abstract. That's why I told you there's specific definitions, but then what does those things really mean? I just like to think of it this way. Energy is the thing in the universe that makes things move. Okay, and so if there's something in the universe that can get things moving, that is called energy. Now there are two types of energy that we can break it down into. Two big classifications, we'll call them, of energy. There is potential energy, okay, and down here I have potential energy and kinetic energy. Now let me start off with kinetic energy. I probably should have put kinetic energy first because I think people can see kinetic energy much more easily. Kinetic energy is the energy of motion. Anything that's moving has kinetic energy. And so, a car going by has kinetic energy. A rock falling has kinetic energy. That movement is using up energy. So anything that has energy of motion. And pretty much just about everything has kinetic energy, if you think about it. I mean, we talked about gases earlier in the year, and these gas law things. Well, these gases have particles bouncing around, right? The gas particles are bouncing around, so they have motion, and therefore they have kinetic energy. But then so do liquids and solids too. They have some type of energy, and so therefore their particles have kinetic energy. Actually, it turns out if there was no energy in something, then the particles would be stopped. And remember that we talked about absolute zero? Theoretically, that object with no energy in it would be at minus 273 Kelvin, which is minus 469 degrees Fahrenheit. So minus 273 degrees Celsius, I should say. Did I say Kelvin earlier? Celsius. And 0 Kelvin. Okay, so absolute zero. So when there is no motion in an object, then it's at absolute zero. So if something, let's say a plate in your home is doing nothing, it's sitting there, it still has kinetic energy in it because it's not freezing cold. If it's at room temperature, that means that the little particles that make up the plate are actually moving enough to keep the temperature at least at room temperature high. If there was no movement of particles inside that plate, then it would be at 0 Kelvin. Now potential energy is the other kind of energy. Kinetic energy is energy being stored. It's energy of motion. There's also potential energy, and potential energy is stored energy. Potential energy is the energy that can be used, but it's not being used right now. Okay. For example, if I take a rock and I hold it 5 feet above the floor, there is a gravitational force that wants to do work on this rock. That gravitational force wants to pull that rock toward the center of the earth. If I let it go, then that rock accelerates toward the center of the earth. Okay, and so that would be using the kinetic energy. But if I hold on to that rock and I don't let it go, then I'm keeping it from doing what gravity wants. So it has what we call potential energy. If I let go of the rock, it'll turn to kinetic energy. But because I'm not letting go, that energy is being stored in there and it's not being allowed to be used. So therefore, we call it potential energy. It has the potential of actually turning into kinetic energy. And that's something that we use with roller coasters. The first chapter of your book here shows a roller coaster. Basically, when you're at the top of a roller coaster and you come down, at the top you have a bunch of potential energy, and as you come down, that potential energy is turned into kinetic energy. And if you add the potential energies and the kinetic energies at any point down that slope, they should equal, they should add up to the initial amount of potential energy. Okay, so just a few things to kind of note on that. All right, so enough of that slide. Let's go on to the next slide. The term heat is also used a lot with temperatures and energy, but heat has a specific definition. First off, what we're going to do is we're going to represent the term heat. We're going to represent it with a lowercase q. So as you can see right here, I'm darkening in the q. It's a lowercase q. So heat is lowercase q. Now, physicists like to use uppercase q, so hopefully that won't be confusing if you end up, finding something later on that that says, oh, hey, heat is uppercase q. But in chemistry, we use lowercase q. Now, if you look at the definition for heat, it's the amount of energy transferred between two bodies with temperature differences. So heat is a form of energy, like work is a form of energy, but they're not the same as energy in general. Heat is a way of transferring energy. Heat is a way of getting energy from one place to the other. And actually what heat is the amount of energy that has been transferred from one place to the other. So let's say that you have a room that is at, we'll say 40 degrees Celsius, which is pretty warm, and another room that is at 30 degrees Celsius. You open the doors, and what's going to happen is the heat from the energy from the warmer room is going to go into the room with the colder room, with the lower temperature. The amount of energy that transfers is called heat. It is energy, but it's energy transferred just based on thermal differences. And the warm room will cool off because it's losing energy. The cold room will warm up because it's gaining energy. And eventually, when those two temperatures of those two rooms meet, now there's no temperature difference. So the energy doesn't want to go from one place to another. So they balance each other out. Both heat and work are methods of transferring energy. A good example of work and how energy is transferred from work is if you've ever blown up a bicycle tire, you have a pump, and you go ahead and push down on the pump. And you'll notice that as you push down on the pump, it might be some work on you, right? It might take some energy. So pushing down on the pump is actually transferring energy from you to the pump. And if you touch the pump later on, after you've been doing this a while, you'll notice that the pump gets warm because some of the energy that you've put into it is now transferred into the pump body. So we have right now at this point definition of energy, the ability to do work, or the potential to do work. We have two kinds of energy, potential energy and kinetic energy, at least two classifications. And two ways of transferring energy. Work is transferred usually done by doing something physical, like pushing on a pump, and it's usually done by applying a pressure on something. Or heat. Heat has energy transfer based on temperature differences. Okay. Now, before we go on, we need to go ahead and learn three other terms so that we can know when we're applying these quantities. The three terms we need to learn are system, surroundings, and universe. Okay. And what you define as your system is going to have an effect on what your answer is for your problem. So first, let's start off with the definition of system. What is a system? A system, as you can see, is a defined area which is chosen as the focus of a process. So a system could be a cup on a table. It could be in a closed box. It could be your car engine and the gasoline in the car engine. It could be an apple. So it really depends on how you define what you're focusing on and how you define that system. So sometimes you want to know, well, how many calories or how much energy is in an apple. We're going to see in a little bit that calories are units of energy. Well, then that's when the apple becomes your system, or a piece of pizza, or like I said, when we're talking about car engines, the car engine with the gasoline in it could be your system, because you want to see how much energy you can put out, so you can see how fast you can go, how far you can go. So that's your system. The surroundings are everything that is not included in the system. And the reason we have to define the system and then the surroundings is that the surroundings are everything that is not in there, and so there's going to be a transfer of energy from system to surroundings, or vice versa. Whatever energy is lost by the system is gained by the surroundings, and vice versa. Which brings us to the term universe. The universe is just your system plus your surroundings. And most of the time, we use the universe as just being, all of the universe as we see it. But sometimes, we can go ahead and make a smaller universe. Like, for example, if something, something occurs in a large thermos flask where no energy can get in and out of the thermos flask, but there is something happening inside the thermos flask. Maybe there's a little box that is having some type of chemical reaction that is creating heat. Then the system might be giving energy to the surroundings. And what we've done by putting all this into this thermos flask, it has to be a large thermos flask, is creating a little micro universe. So usually, though, the universe is pretty much what we think of as the universe. The system is what we're looking at. The surroundings is everything. But sometimes we can also define the universe as something smaller. So those are a few terms that we're going to be using as we go through the chapter. Another couple of terms: exothermic and endothermic processes. An exothermic process is one where energy is leaving the system. The prefix exo means out, and thermic means refers to energy. So whenever you have energy leaving a system, then you have an exothermic process occurring. And generally, these exothermic processes occur when the energy leaves as heat. So for an exothermic process, Q has a negative value. Because if you're thinking of the system, let's say the system is a cup of hot water, and that hot water, it cools off. That must mean that energy has gone from the hot water, it's gone out into the surrounding air, the surrounding atmosphere. So that cup of hot water, the actual water, has lost energy, and it's lost energy because the energy went from the hotter water to the cooler air around it. So the Q you're going to have is a negative value, and your system loses energy. That's only because I defined the system as my cup of water. An endothermic process is one where the energy enters the system. If I'm warming up the cup of water, then energy goes into it. So we're gaining energy as heat, and your Q has a positive value. We are gaining heat. And we are gaining energy as heat. Oops, what did I just do? So the system gains energy. Okay, so those are two other terms that we'll be using a lot. Now let's take a look at some units of energy. The first unit we're going to look at is the calorie, and I'm sure you guys are very familiar with the term calorie. People are always counting calories. So what is a calorie? Right? Because you look on some packaging from food, and you see that the I don't know, spaghetti has, you know, 300 calories. But what does it mean to have that many calories? Okay. Well, it's how much energy is in that, because what we do is we eat food, and we go ahead and get food from substances that have energy in them. Uh, Carbohydrates, proteins, and fats all have energy in them, and that's why we eat, so we can get that energy. So we measure those that energy in calories. And calorie, so you know, is an English unit. You know, it's like, you know, yards and feet and miles and inches and that type of system. Right? So it's an English unit of measure for energy. And a calorie is equal to the amount of energy required to raise 1 gram of water 1 degree Celsius in temperature. So if you have 1 gram of water and you heat it up 1 degree Celsius, it really doesn't matter if it was from like 1 degree to 2 degrees or 47 degrees to 48 degrees. As long as you heat up for 1 degree Celsius, however much energy that took to warm that 1 gram of water up 1 degree Celsius, that is a calorie. Okay, so we've defined it as that. And as I mentioned earlier, among other things, calories are used to measure the amount of energy in food. Now, just to let you guys know, on the packaging of foods, they don't really use calories. They use kilocalories, but they don't count them as calories. So you'll recall that the prefix kilo means 1,000, so a kilocalorie is equal to 1,000 calories. And the calorie with a capital C, notice here this one has a capital C as opposed to lowercase c, is what they use on food labels. And what they've said is, well, we're going to put a capital C for calorie, and that's actually going to be equal to a kilocalorie. Now, why do they do that? They do it to not freak people out. It's mostly marketing. But they go ahead and they, if you got a Snickers bar and your Snickers bar says, oh, there's 220,000 calories in this. You might go, oh my God, that's so many calories, I won't buy this. But that's true. A Snickers bar, if it says it has 220 calories, it's actually 220,000 calories. The calorie on the Snickers bar is a capital C, which is equal to a kilocalorie, 1,000 calories. And they do it so that you won't freak out and you realize that you're eating hundreds of thousands of calories. It just looks like hundreds of calories. Still the same, but marketing, try to make it look not as scary. Okay, so calories are units we will use. But just kind of like feet and miles, and pounds. Those are units that we're used to using, but they're not the ones that we use the most. The ones that we're going to use more, because they are part of the metric system, or at least the SI system, International System of Units, are what we call the joules. And here I have the term joule highlighted. So a joule is a unit of energy that was derived from the work equation. Okay, so these are the units that we would get when we calculate work. We would end up with joules. Okay. This is named after a guy named James Prescott Joule. James Prescott Joule, I'll put that up here. James Prescott Joule. And James Prescott Joule, he did a lot of studies on energy. It's kind of like Torr was named after Torricelli, and the Pascal was named after Blaise Pascal. So we have a unit here of a joule. And if you go ahead and if you multiply 1 Newton by 1 meter, I'm missing a meter right here, you get a Newton times a meter, which they've renamed a joule. So the amount of energy it takes to push 1 Newton 1 meter is a joule. Turns out that there's a relationship between calories and joules. 1 calorie is equal to 4.184 joules, and that's a calorie with a small c. So, that 1 gram of water being warmed up And of course, a lot of what we measure, um, joules are kind of small. So a lot of what we measure has a lot of joules in it. So we use the term kilojoules a lot, or the units kilojoules a lot. Remember that a kilojoule is 1,000 joules. Okay, so those are the two main units we'll be using, calories and joules. You may not, you may have heard of other energy units like BTUs, which are British thermal units, and there's other different units that you can use for energy, but in science, we tend to use these more. Okay. Now let's come to the term heat capacity. Okay. What is heat capacity? Heat capacity is, as you can see in the definition, the amount of energy required to raise the temperature of an object 1 degree Celsius. Okay. So if I have, let's say, a cup of water, how much energy it takes to warm that cup of water up 1 degree Celsius, that's the heat capacity of that cup of water. Okay. Now there's another term, sounds like heat capacity, but this one's specific heat capacity, and it's going to be represented by the capital letter C. The specific heat capacity is how much energy is required to raise 1 gram of a substance 1 degree Celsius. Okay, so if you want to, specific heat capacity is not related to a whole object, but it's more like looking at a substance and see how easy it is to heat up. The larger the heat capacity, the harder it is to heat up, because it takes more energy to raise that 1 gram. So we're taking 1 gram of every substance, 1 gram of water, 1 gram of alcohol, 1 gram of iron, 1 gram of copper, 1 gram of zinc. And if you want to get an idea of how easy it is to heat it up, you look at a specific heat capacity. Here's the formula, and we'll be using this formula in our sample problems. It's good to know. Oops, got ahead of myself there. C here is your specific heat capacity is equal to Q, which is the amount of heat required to heat this up, divided by M times delta T. Right, this delta T right here, this delta T is the change in temperature. So Q stands for heat, M stands for mass, and delta T is your change in temperature, how much the temperature has changed. One thing to note, when delta T is positive, it means you warm something up, and when delta T is negative, you've cooled something down. Okay, so it's changed. Whenever we use the Greek letter delta in science, it means how much something has changed. So you can put the delta in front of just about any letter or any quantity, and that'll tell you that we're looking at how much that quantity has changed. So delta T here is equal to T final minus T initial. Tf is your final temperature, Ti is your initial temperature, and it will work accordingly based on what your initial and final temperature was. If you warm something up from, let's say, 40 degrees to 50 degrees, so your initial temperature was 40 degrees, your final temperature was 50 degrees. Then you put the 50 first, minus the 40, 50 minus 40 is positive 10. So your delta T is a positive 10. But if you cool down something from 50 degrees to 40 degrees, then you would go, you'd put the 40 degrees, your final temperature was 40, your initial temperature was 50. 40 minus 50 is negative 10. Okay. And here with energies, as you're going to see, it's really important to keep track of your positives and negatives, because sometimes quantities require you to tell whether something is exothermic or endothermic. And if the Q ends up being negative, it's exothermic. The Q is positive, it becomes endothermic. And these signs go along with the way that these things work. Now, one thing to note is we were mentioning is that the specific heat capacity is related to a gram of a substance. It's kind of like density, where it's specific to a certain substance, and it's in density, it's per milliliter, so that we can compare 1 milliliter, how much 1 milliliter of each substance weighs. Heat capacity is a lot like that. Specific heat capacity is like that. It's comparing how easy it is to warm up 1 gram of a substance. Turns out that the larger your heat capacity, the harder it is to warm it up. The smaller the specific heat capacity, the easier it is to warm it up because it takes less energy. Let's take a look at some sample ones. And as I mentioned, substances with small specific heat capacities warm up much more quickly. Larger specific heat substances resist temperature changes. So here I have a little table that's in your book in section 1 of chapter 16. Can't remember the exact page. And the specific heat capacity for water is 4.184 joules per gram degree Celsius. So you notice the units are joules per gram degree Celsius. That means that in order to warm up 1 gram of water, 1 degree Celsius, it takes 4.184 joules. And that's because, remember, the definition of calorie was how much energy it takes to warm up 1 gram of water, 1 degree Celsius. And a calorie is equal to 4.184 joules. So it kind of works out that way. Now, water in its ice form warms up much more quickly. It actually has a specific heat of 2.03 joules per gram degree Celsius. In other words, in order to warm up ice 1 degree, 1 gram of ice warms up 1 degree when it takes in 2.03 joules. Ethanol, grain alcohol, 2.44, warms up much faster than alcohol does, basically almost twice as fast. And look at these metals. You know that metals warm up much faster. You leave an iron rod in the middle of, on the cement on a hot summer day, and you put a cup of water next to it. When you come back in 3 hours, you touch the metal rod, it's going to be much hotter than the cup of water. Why? Because their specific heat capacities of metals are much smaller. Aluminum is 0.897, granite, which is actually more of a rock, 0.803, iron 0.449, lead 0.129. And so this is how much energy it takes to warm these guys up. Warm 1 gram of the substance, 1 degree Celsius. The smaller number you have, the less joules it takes to warm it up 1 degree Celsius. Okay. This idea can kind of also explain things like, well, why is the coast being near the beach cooler in the summer and actually warmer in the winter? Most people don't realize that because sometimes the beach can get a little chilly with the winds, but when it's not windy, it tends to be warmer. If you look at the high temperatures during January, February, you'll see that the more inland you go, the colder it gets. The more closer to the coast you are, the less cold it is. I don't want to say the warmer it is, less cold it is. That's because water has a cooling effect. The air has a certain temperature above the water, and when the temperature is higher above the water, then the energy goes in, or the heat goes into the water, and it cools the air in that general area. And that's why you go down to the beach and it's cooler than it is here in Montebello. Even in the summer, even in the winter, that water is having an effect on the atmosphere. When it's cold outside, the air is cold. It's colder than the water in the ocean. Well, the heat transfers from the water up into the atmosphere and it warms it up a little bit. Because it's got such a large specific heat capacity, the water doesn't change temperature that much, but it changes the temperature of the air more. So it has a bigger effect. Okay. All right, and one last slide on this presentation right here. There's a thing called the law of conservation of energy. And we're going to be using that to kind of guide a lot of our problems and the way we would solve problems. The law of conservation of energy is a lot like that law that we saw earlier in the year, the law of conservation of mass. Stated very similarly, except that it's talking about energy versus mass. Remember we said that earlier law of conservation of mass says that mass cannot be created or destroyed, it can only change forms. And basically from that we got the idea that the mass in a chemical reaction, the mass of the reactants have to equal to the mass of the products. Well, as far as law of conservation of energy is concerned, same idea. Energy cannot be created or destroyed. All the energy in the universe is already out there. It's just changing forms. It can only change forms. One way we have of showing that is by using this equation right here. Q subscript SYS stands for Q of the system. The heat of the system is equal to the minus Q of the SURR. That's the surroundings. And basically what this is saying is that any heat that has been lost by the system is gained by the surroundings. Or any system that has been gained by the system was lost from the surroundings. You may look at that equation and go, wait, that looks kind of weird. It looks like the Q of the system is always positive, which would make the system always endothermic, and the surroundings negative, therefore the surroundings would always be exothermic. That's not the right way of looking at that. This negative right here in front of the Q surroundings, I could have put it in front of the system, right? And I can multiply both sides by -1, and the negative would go on the other side. So really it could go on the left or the right. What that negative is saying is right there is whatever the Q of your system is, whatever the heat gained or lost by the system, the sign of the surrounding is going to be the opposite. It's going to be the negative, right? So if your Q of your system is -300 joules, then the Q of the surroundings is negative 300 joules or positive 300 joules. So if your Q of your system is negative, then the Q of the surroundings is positive. Whatever was gained by the surroundings was lost by the system. And when your Q of your system is positive, then your Q of your surroundings is negative. So if the system's Q is 400 joules, that means it just gained 400 joules. Well, where did it get them from? It got them from the surroundings. So therefore, the Q of the surroundings is negative 400 joules. All right, that's as far as we're going to go today. This whole change in enthalpy thing, we'll talk about what enthalpy is next time. Okay, so let's stop here for today. There is another video showing sample problems, so you might want to kind of look at that. This video here looks like it's about 37 minutes. You don't have to watch it all in one shot. Of course, I say that at the end of the video. But one thing I like about putting up these videos is that you can kind of watch 10 minutes, then another 10, and eventually get all through this as you need. Okay, so we'll come back to this PowerPoint presentation, and we'll continue from here when we deal with the second section of chapter 16. These other videos will show how to do the problems, mostly the problems related to specific heat capacity and this equation on a separate video. Okay.